So, yesterday we have discussed about heat engine. Okay. So, today we are going to discuss about a refrigerator. Okay. Or heat pump. I'll explain what is the difference between a refrigerator and heat pump. The way they work is same. Only difference is what is the purpose. Okay. So, I'll explain that what is refrigerator and what is a heat pump. Okay. So, as I said, refrigerator is just a reverse of a heat engine. Like as you can see here, heat engine work is done by the system on the surrounding. Okay. So in case of a heat engine, you had a reservoir. Okay, you had a reservoir, and the temperature of this reservoir was T1. Temperature of this is hot reservoir or the heat source. This is the cold reservoir or the heat sink. Okay. So you take some heat from the hot reservoir or the source, the working substance, the gas or whatever. It takes that heat, okay, does some work and throws away some heat to the sink or the cold reservoir. Okay. So that is heat engine. So if we say the refrigerator is reverse of a heat engine, what does that mean? So these three arrows, these will just reverse its directions. So like Q2, the arrow direction is reversed. Q1, arrow direction is reversed. W, arrow direction is reversed. So what is happening here? This is your uh, the cold reservoir. Okay, this is your outside surrounding. Okay, so the difference is like you imagine this is your fridge. This reservoir is nothing but your inside of your fridge. Okay, so this is nothing but your interior of the fridge or the volume of the fridge or whatever. Suppose we are telling that capacity of the fridge is 165 liter. What does that mean? It means the volume enclosed inside the fridge is 165 liter. Okay. So we are trying to cool that 165 liter of volume. Okay. So you have double door fridge or triple door fridge. That means you are maintaining different temperature at different chamber. So you are maintaining uh, different temperature. You are maintaining different temperature in the different chambers of the fridge. Um, and suppose you are telling you it's a high capacity fridge, low capacity fridge. It is all depend. It's the volume. How much volume you are cooling. Okay. So, so you are taking away some heat from inside this refrigerator chamber. Okay. So you are taking away some heat. So this what is happening in the refrigerator? It is against the law of nature. Okay. From you are taking away some heat and throwing it to the surrounding. So you have a fridge in the room. Okay. So when you have a fridge in the room, some heat is thrown to the room. So the room may get heated because it is taking the heat from inside the refrigerator and throwing to the room. Okay. So you can imagine this is your refrigerator inside the refrigerator, and this is outside the refrigerator or the surrounding or the room. So you can say. So here the temperature is again T2. Okay. So when we are throwing heat to a hotter surrounding, that means it's against the law of nature. Heat flows from high temperature to low temperature. So that is the actual law of nature. But when you are throwing it to low temperature to high temperature, you have to do some work. Okay. So here the work is done on the working substance. Whereas in heat engine, the work is done by the working substance on the surrounding. Like the piston, there is some expansion, and because of the spark or whatever, there is a power stroke. So during the power stroke, there is some expansion happening. So that piston is doing work on the surrounding. Whereas here the work done is on the working substance. Okay, so here work is done on the surrounding. Here work is done on the working substance. Okay, so that is the direction is reverse. So that's why we call refrigerator is just reverse of the heat engine. Heat engine, heat engine work is done by the system on the surrounding. A refrigerator work is done on the system by surrounding. That is refrigerator. Work is done on the system on this working fluid. Work is done by the surrounding. Okay, so that is the difference between refrigerator and heat engine. Okay. So then again, we are talking about not only refrigerator, also we are telling about heat pump. Okay. So heat pump, what does heat pump actually do? Like if your concentration is, hmm, if your concentration is, for example, like this is example of a heat pump. So you are not concentrating on you are rather than concentrating on this area. If you are concentrating on this area, okay. So you want to heat a portion of the building, okay. Suppose in Western countries it happens like the whole building is very cold, okay. So you want to heat a, where you are staying in that area, you want to hit that person, okay. So in refrigerator you are concentrating on this, whereas in heat pump you are concentrating on this. So but the working is same, but here your area of concentration is the cold reservoir, here your area of concentration is where you are hitting, okay. So refrigeration, you are heating, you are cooling that the interior volume of the refrigerator. Whereas in heat pump or the blower or whatever, the whole building is cold. You want to heat a portion of the building. So you are taking some heat, okay. Then you are doing some work and you are throwing that heat to that portion of the building, and that portion of the building get heated. So that is the cycle, the process remains same. Only the area where you are concentrating is different. That's the difference between heat pump and a refrigerator. Okay. So that's where you are concentrating. That is different. Okay. Um, so heat pump, refrigerator, similar. The purpose may be different. Heat pump, heating portion of a room when the outside temperature is less. In Western countries, that happens. Okay. So now let us discuss about what are the different components of a refrigerator. Okay, so the refrigerator it goes through four different processes. Okay, what are the different components of a refrigerator? Like you may be knowing that the refrigerator has a compressor. That outside the refrigerator, below the chamber or the side of the chamber, there is a compressor. So that compressor takes some work actually. So that compressor is driven by the electrical energy, and that compressor will be normally it will be driven by a motor or whatever, right? So compressor, there there are different work taking devices like in compressor, pump. These are work taking devices. Okay, like compressor in your when you are giving pressurized air to, like giving pressurized air for vehicles tire, you are using a compressor. Okay, so compressor, pump is to pressurize liquid. Okay, so these are all work taking devices, but they are the reverse of compressor is turbine. This gives work, whereas compressor and pump, it takes work. So compressor is related to gas or air or whatever. Pump is related to incompressible fluid like water or whatever, right? So it has a compressor. Then after compressor, it has a condenser. And then after condensation, it has a throttle valve. Then after throttle valve or expansion device, it has a evaporator. So it has four different components: the evaporator, the compressor, the condenser, and the throttle valve. So what exactly these things are doing? So you imagine, start from the like the evaporator. Okay, you start from the evaporator. So this corresponding to this schematic diagram, there is in thermodynamics there is a corresponding P and H diagram. Okay, so this is in the y-axis you have pressure, in the x-axis you have enthalpy. Okay, so this is like this is this line actually. If we yeah, so I have drawn it here. So I have okay. So done. Okay. So I have already explained about it. So now let me rub it up to draw the corresponding pH diagram of for a refrigeration cycle. Okay. So pH diagram. So I have drawn it, but let me explain it one more time. Okay. So this is basically your pressure in the y-axis, and H is called enthalpy. Okay, enthalpy means the heat content. Okay, suppose in a if there is in a isentropic process, when there is no heat addition, the enthalpy remains constant. Okay, so enthalpy is the heat content. Just remember that much. Okay, so in pH diagram, it looks like something. It is this line is called a saturation line. Okay, so what I was saying was all gas, Carnot cycle, what I was saying. But for steam and other like the refrigerant, it 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 the working substance changes its state. It becomes liquid. Sometimes it is vapor. Sometimes it will liquid plus vapor like that. So this is called the saturation line, right? This is saturation line. And the left side you have liquid. Okay, on the left side. In the right side you have vapor. So vapor. So when the liquid converts to vapor, that process is called vaporization. Okay, and when vapor gets converted to liquid, that is called condensation. Okay, so and when solid gets converted to liquid, that is called melting. We are not dealing with melting here, we are dealing with vaporization and condensation. Okay, so like how do we start the process? Like say what happens? Let us say we start from the compressor. Okay. So here compressor, before it enters the compressor, the point is one. Okay. Corresponding to one, we have this point one. Okay. So corresponding to this point one, we have point one here. So before entering the compressor, it is a low pressure, low temperature vapor. Okay, it is a low pressure, low temperature vapor, and it is on the saturation line. Okay, so that is the point one. Now in the compressor, what happens? It is getting compressed. So when it getting compressed, okay, so it is a isentropic compression. Okay, so the the line, isentropic compressor line, it will be something like this. Okay, so isentropic compression. Okay, so from one, after the compressor, this goes to point two. So it is a beyond the saturation, super saturation region. Okay. So this is low pressure, low temperature vapor. After compressor, it will become high pressure, high temperature vapor. Okay. The pressure compressor increases the pressure, and because of compression, the temperature also increases. Okay. So low pressure, low temperature vapor becomes high pressure, high temperature vapor. Okay. So you arrive at point two. Okay. Then from point 2 to 3, it is condensation. Okay. So it will condense, the vapor will condense, then it will reach the saturation line. So here, this is actually vapor. Okay. Then from this point to this point, condensation, actually during condensation, there is no change in pressure. It is a constant pressure process. Okay. So, so from here to here, actually this area is liquid plus vapor. When it is condensing, it will have partly liquid, partly vapor. Okay, so this is your liquid plus vapor. And then 1, 2, then after the condenser, the point is 3. Okay, so between 2 to 3, the supersaturated vapor, then it will become saturated vapor, then in between it will become liquid plus vapor, then all vapor will get converted to liquid, and at point 3, it will be just the liquid. So what is so which is undergoing these changes? This is nothing but the refrigerant. Okay, so there will be some piping. Okay, there will be some piping through which this refrigerant will be flowing. Okay, so the refrigerant is what we are studying about the greenhouse gases, that chlorofluorocarbon and all. That is the refrigerant. Okay, so this. So it comes to the point 3. Okay, then from point 3 to 4. Okay, so this is the drop in pressure. Okay, this is drop in pressure, and it happens in a valve that is called a throttle valve. Okay, so these are just schematic representation. You can have another representation how actually a condenser looks like, how actually a evaporator looks like. Okay, so these condensers and evaporators are nothing but some lines, some pipes like this. Okay, so evaporator, condenser, they look like this. And compressor you might have seen already. And throttle valve is also some kind of where that is called throttling. Okay, so during throttling, what happens? The pressure drops. Okay, the pressure drops, but there is no change in enthalpy. Okay, so there is no. It's a means there is no change in heat content. Okay, so that's why the enthalpy remains constant. Okay, so this is in the throttle valve. It's a isoenthalpic process, and in the compressor it is a isoentropic process. Okay. So now from 3 to 4, there is a sudden pressure drop. Okay, that happens in the throttle valve. Then once it comes here, it is again in a liquid plus vapor condition, right? So liquid plus vapor condition, then from 4 to 1 it goes. So here it will take some heat. Evaporator, it evaporates. So it has to take some heat. So let us see that heat is Q1. Okay. So and in compressor, there is some work done. Okay. It will take some work. Okay. It will the compressor will take some work, and in condenser there will be the it will reject some heat to the outside. Okay. So because it is condensing, it is becoming liquid from vapor. So whatever latent heat or whatever is there, or this from here to here, it is latent heat and other heat. It will be thrown to the surrounding. So evaporator takes it, condenser throws out heat and throws heat to the surrounding, and compressor takes work. Okay, so that is how it is happening. So you can like in in heat engine we call something as efficiency of the heat engine. Okay. In heat pump or refrigerator, we call it as coefficient of performance. Okay. COP, coefficient of performance. Okay. So what is means how the refrigerator is functioning. Okay. That will be a specification. Like you want your COP or coefficient of performance to increase. Like in efficiency, you want to increase in refrigerator heat pump, we call it as coefficient of performance. Okay. So COP or coefficient of performance is nothing but Q2 by W. Okay. So like what actually you want to achieve? Like you want to cool it. Okay. So actually this in the condenser, In the condenser, you are cooling it. So, the more is the Q2, okay, more is the cooling effect, right? So the Q2, and to cool it, you have to do some work W. Okay, so you are doing some work W. Actually, yeah. So where Q2 is the heat extracted from the cold reservoir. So why you are putting Q2 in the numerator? Because Q2 is the amount of heat that is extracted from the cold reservoir. That means from the refrigerator chamber, you are extracting heat Q2, and that Q2 is used to like so from the refrigeration chamber, you are extracting heat Q2. Okay, and it is being thrown to the surrounding. Okay, from the refrigeration chamber, you are extracting heat Q2. Okay, and W is the work done on the system. W work done this on the system. Uh, uh, System. Okay, on the refrigerant system is nothing but the refrigerant, right? So and for heat pump, okay. So for refrigerator, this Q2 is important. Okay, how much heat you are extracting from the interior of this thing, interior of the refrigerator. So that is for uh, refrigerator. Whereas for heat pump, this coefficient of performance, the COP for heat pump will become Q1 by W actually. Q1 by W. Right? Because in for heat pump, Q1 is important, right? So for a heat pump, actually, your area of interest in heat pump is this: how much heat is going to that hot portion of the building. So your concentration is on Q1 in heat pump, whereas in case of refrigerator, your concentration is Q2. That's why for coefficient of performance for the heat pump, it is Q1 by W, whereas like heat pump, whereas coefficient of performance for refrigerator is Q2 by W. Okay, so in refrigerator, this is your area of interest. Okay, so you are extracting heat Q2. Okay, so from there you are extracting the heat. Okay. So when you are extracting the heat, this refrigerant is becoming kind of uh, vapor to liquid when heat is being extracted. Okay, and in evaporator, the it is becoming liquid plus vapor to vapor. Okay, so coefficient of performance and this. So you know in like W is like del Q or whatever. That remains the same. First law of thermodynamics. So your W is equal to, like say, Q1 minus Q2. That you know. Okay. So if you change that, then what will become the COP? COP for heat pump is equal to say Q1 by Q1 minus Q2. Right. And for a COP for a refrigerator will become Q2 by Q1 minus Q2. Okay. So this mm, uh, so in case of Q1 is definitely more than Q1 minus Q2. That means coefficient of performance of heat pump can be more than one also. So COP can be more than one. So in heat engine, we say heat cannot be fully converted to work. However, a refrigerator cannot work without some external work done on the system. That is, the coefficient of performance cannot be infinity. Okay. So, okay. Q2 is the heat extracted from the cold reservoir, and W is the work done on the system, the refrigerator. For heat pump is defined by W. Note that while when the efficiency can never be greater than one, whereas uh, whereas heat pump coefficient of performance can be greater than one. Okay. Uh, in heat engine, heat cannot be fully converted to work. Likewise, in a refrigerator cannot work without some external work. So, a refrigerator cannot work without the compressor. Okay, done on the system. So, and the coefficient of performance also it can be greater than one, but it cannot be infinity. Okay, so because W cannot be zero. Okay, coefficient of performance can be greater than one, but it cannot be infinity because you have to take some work. So coefficient of performance can be greater than one, but it cannot be infinity. That is related to again second law of thermodynamics. Efficiency of heat engine cannot be one, or the coefficient of performance of heat pump cannot be infinity. These are all related to second law of thermodynamics. Means you have to take some work to do that. Okay. So that's all about the refrigerator and heat pump. Next, we'll be discussing about second law of thermodynamics because I have given some pointer to second law of thermodynamics. Why efficiency cannot be one? Why is it has to reject some heat to the surrounding? So those points we'll discuss in second law of thermodynamics. Okay.